Welcome to our SiC GaN WBG Expert Round Up discussion. We will talk about everything you need to know about efficiency that drives the future. In this discussion, we have two of our EBV experts talking about advantages, practical examples, and much more. I would like to introduce Karl Lehnhoff, the EBV Director for the Market Segment Industrial, and Milan Ivkovic, the EBV Director for the Technology Segment Analog and Power. Let's get started. Karl, thanks for joining the discussion. The first question is for you. WBG technology is on the way from early adoption to mass market. Now we see in many applications that in new designs, WBG is used. What are the applications that you see?
We as EBV Electronic start already to promote SiC MOSFET in a white paper in October 2013 for a motor integrated inverter. In the following years, we have had designs in servo drives, photovoltaic inverter, and uninterruptible power supplies. Also, wide band gap is used in e-vehicles. Good example here is Tesla. Nowadays, wide band gap makes sense in all kind of power supplies and inverter, like e-vehicle charging, wind inverter, wireless charging, and any kind of drives, not only servo drives.
And what has changed? What now facilitates more widespread use of SiC and GaN?
The climate change has also here a big influence. We have new regulation in place which drives the application to reduce the CO2 emission, and so we have to reduce the used power and losses for all applications. A good example here is the e-vehicle, and in industrial, the energy efficiency directive for drive inverter. With this, the quantities in wide band gap increase and the prices are going down. Also, we see a big change in the thinking in the R&D process. In the past, only price by components was noticed. After that phase, there was a change to system cost, and nowadays we discuss life cycle cost. With this cost of the energy consumption during life cycle will have a big influence. To give you an idea, in an electric motor, only 1% of the life cycle cost comes from the purchasing price. 99% of the life cycle cost results from operating and maintenance. With this change, wide band gap makes more sense in many applications.
Milan, thank you also for joining the discussion. Here's your first question. What are the general advantages of WBG semiconductors?
Well, these semiconductors can bring advantages both on component and on system level. So wide band gap as a switch allows for faster switching transition, which is bringing lower switching losses. On the other hand, the higher breakdown field voltages field in these materials allows us to have shorter channels of the devices, which is bringing a lower RDS on state, which means lower conduction losses. So having these two features combined, we have wide band gap as a switch that is closer to an ideal switch, and this means less losses on the switch level. On the other hand, the higher switching frequencies allows to usage of smaller passive components, and smaller passive components brings the whole system smaller and cheaper at the end. Also, lower losses are requiring lower cooling effort, so our cooling system can be smaller, so less restrictions on cooling. In some cases, we can even switch from liquid to forced air cooling, or even from forced air to fanless cooling, which is introducing more reliability in the whole system. So, and at the end, together with smaller passive, it brings to lower space and weight of the whole system. And at the end, as summarizing, so the advantages are definitely higher efficiency, smaller size, and smaller cost of the system overall.
And to what extent will system cost reduce with SiC and GaN?
So different applications have different kind of calculation, but we can take solar as an example. So let's say we take one solar inverter of 75 kilowatt of installed power that weighs about 75 kilogram for easier tracking of numbers. That means that we have a power density of 1 kilowatt per kilogram. This is implemented today with, for example, silicon IGBT. If we introduce silicon carbide MOSFETs, then we can reach power density of 1.7 kilowatt per kilogram, let's say. And if we make some rough calculation, then we can either have the same amount of installed power of 75 kilowatts into much smaller device that is like 40 kilogram, or we can keep this 75 kilogram equipment and install roughly 130 kilowatts, something like this. So these numbers that I gave are just illustrative, but they're based on real solar inverter example. And this is bringing us to conclusion that we can, to ideas that we can either minimize transportation or installation effort, or we can maximize installed power in the predefined installation places. And if you take this solar as example, you can imagine two technicians that are managing 75 kilograms alone. And today, this is much more power that is installed in the predefined space. So obviously, this benefit is coming from lower switching losses and higher speed of wideband gap. Different kind of calculation, which Karl already mentioned, but in this case, we can also think about EV charging or UPS, where you actually, at the end user, you have buying and selling energy. So every kilowatt that you dissipate in EV charger station is money that is wasted by operator. So, and when we calculate number of operating hours during the lifetime, we quickly are seeing how silicon carbide, in this case, is bringing to less operational expenses and at the end, the total cost of ownership of the equipment.
And how do SiC and GaN power electronics fundamentally differ? What are their respective advantages?
Yeah, so these both have fundamental difference from silicon, that they have higher band gap voltage. They have also some other differences from silicon, but they also differ from each other in specific features. For example, silicon carbide is a vertical MOSFET, and it is implemented in planar or trench technology, depending on the manufacturer. But gallium nitride is a lateral device, and it is based on high mobility 2D electron gas. And still, different manufacturers are using different technologies to produce GaN, which is then bringing different behavior in end applications from the point of user. But these specific features that they have, they position them in different kind of applications. For example, silicon carbide has a much higher thermal conductivity, material itself. And then this is a good candidate for higher power applications. And the trend is to replace IGBTs in 1200 and above volts range, and silicon junction and super junction silicon in 6 and 650 volts range. Gallium nitride, on the other hand, is allowing for much higher switching frequencies, which is then good choice for application where the highest power density is really a must. This is like telecom power supplies or server power supplies and so on. GaN has also some other nice features like zero reverse recovery charge, which is essential for hard switching applications, and it has very low output capacitance and very linear, which is then good fit for Class D audio, for example.
And what do users of SiC and GaN power electronics need to keep in mind when designing their systems and devices?
Yeah, so definitely, as we said, this is different from silicon, so no one can expect one-to-one replacement. But on the other hand, these new technologies are enabling new topologies into power electronics, and like all of these benefits are coming on expenses of design effort and different design approach. But the good point is that when these design procedures or knowledge or know-how is adopted, then it leads to normal routine like we have today with silicon. Key challenges are definitely faster switching speeds, which is bringing to different EMI footprint. It is different driving. We have different failure modes, definitely. We have to take care about different short circuit protection, and maybe to think about robustness as especially for GaN, it can be slightly different comparing to MOSFET or IGBT. As I said, this is different structure inside. Also, for quality departments, they can challenge reliability because these are new technologies. And also it can be a challenge like, okay, now we have to make different qualification tests for our end equipment. But luckily we have a lot of solutions today to help designers. We have numerous white papers, especially silicon carbide is on the market and in research for a while. We have application notes, different kind of customized drivers are designed and produced, and of course we have a lot of evaluation boards for different applications, which can help designers to try before buy or even to try before deciding going to wide bandgap direction. Special care here also, we have to mention that driving is different. For silicon carbide, it's more similar to today's IGBT and MOSFETs, with special caution to be taken on short circuit protection, dead time, Miller clamping, under voltage lockout, or high common mode rejection ratio, because everything is coming from high switching speeds. And then we have to take care about isolation barriers that we had today to isolate floating signals. Now with much faster signals, we have very high common mode signals of high change rate. On the other hand, GaN is a bit different in some appearances, I would say, and technology. This is current-driven device, so driving technology philosophy is a bit different. But we have also drivers that are customized for GaN driving, which is then really easing designers' job to drive GaN. We have also some GaN devices that are coming cascoded with low voltage MOSFET. Then we are driving simply a low voltage MOSFET and GaN is driven inside. And on the top of that, we have devices that are integrating both GaN switches and GaN drivers, or even a GaN switch and flyback controller. So from outside, from the driving point of view, we don't see that the GaN is really inside. And finally, we have a lot of new packages that are designed, especially for these high-speed devices, to use the full potential of high-speed switching and to ease PCB routing, everything in a way to minimize EMI reduction, to minimize EMI generation, which is here the high switching frequencies present for sure.
And Karl, back to you. Where can interested parties find information on WBG technology and available solutions?
We post regular wide bandgap information in social media and on our EBV blog. Also, you'll find useful information on ebv.com. But if you are interested in the latest trends and news, you should get in touch with us. Our field application engineers are system and technology specialists and are well trained by our suppliers on all new technologies and new parts. We can answer your questions like what to use and how to use. We are aware on new parts before they are introduced to the market. In addition, we have our market segments. They know what the newest trends in the markets are, know the related application and the newest parts for that. This knowledge we transfer on regular basis to our field application engineers and account managers. Also, we organize regular webinars, seminars, and be present on fairs. Even during these times, we do all this in a virtual form.
So thank you, Karl and Milan, for joining in the discussion and for sharing your expertise.
Thank you.
Thank you.
Bye.
Bye.